Hi, my name's Jack and this is an investigation into the efficacy of variable angle of attack motorcycle winglets. Motorcycle winglets directly fixed to the front fairings on modern race motorcycles address the problems of high-speed instability due to drag acting on the rider and the motorcycle pulling the forks up, braking stability and wheel lift under acceleration. Typical motorcycle winglets work by producing downforce, often at speeds in excess of 250 km an hour. Which is a much greater speed than many older or smaller capacity road and race motorcycles can achieve. This investigation assesses the efficacy of variable angle of attack winglets for use on motorcycles with lower top speeds. By altering the angle of attack of the winglets, downforce can be produced more efficiently over a range of speeds by the winglet orientation being optimized for the specific speed that the motorcycle is traveling. Winglets are most effective when the motorcycle is ridden in a fashion concurrent with the technique displayed by the fastest motorcycle racers, such as this here. That is leaning off the motorcycle with one's body to lower the combined center of gravity of both the rider and motorcycle. This technique allows less lean angle compared to staying upright on the bike, keeping the contact patch of the tyre closer to the center and allowing the suspension to work more effectively. The style of riding has an even greater advantage when combined with winglets, as the vertical downforce component generated from the winglets will be greater than the lateral downforce component. As you can see here, if you can imagine, as this stands up and the winglets are horizontal, the vertical component compared to the lateral component is going to be greater the more upright the motorcycle is. Another perceived benefit of winglets, depending on their placement, is a potential low pressure region of air at the exit area of the fairing behind the radiator, helping to suck air out from behind the radiator to create a better exit condition and increased cooling potential. The bottom figure, taken from a study that suggests a pair of winglets from the Kawasaki H2R fitted to a generic motorcycle could produce as much as 12 kilograms of downforce at 200 kilometers an hour. As can be seen here, when the wingleted case is compared to the non-wingleted case, the addition of winglets contains a lot more blue around the lower section and the radiator exit, which indicates lower pressures. The darker the blue, the lower the pressure. And this is due to the suction from the bottom surface of the winglet. Photogrammetry is the process of gathering measurement information for an object by measuring the difference in position between a series of photographs from differing perspectives of the object. The software is then used to process the images and construct a model of the object. The data gained from the photogrammetry process is often used to create 3D models of objects or even maps. Meshroom from Alice Vision is a free and open source photogrammetry program and the one that was chosen for use in this project. The motorcycle used for the process was a 1996 Honda RVF 400, which is indicative of an older, slower and smaller capacity sport motorcycle. Once the motorcycle was generated in Meshroom by the photogrammetry process, the geometry was exported as a wavefront file into an editing program called Blender for further processing. Shown in this photo here is the initial environment which the photos were taken. It contains a lot of high gloss surfaces. It was on a sunny day. There's plenty of shadows and it produced a subpar model. So learning from the first attempt, the second attempt photogrammetry, the environment was undercover on an overcast day. However, it still contained a lot of high gloss surfaces and shadows. The Blender model produced is still missing significant geometry, most of the fairing at the bottom and the side here. The final photogrammetry environment was on a relatively sunny day under the cover of a roof, with lighting coming in from the sides. This threw far fainter shadows. Masking tape and flour were used to cover the glossy painted surfaces of the motorcycle, and distinctive features were added to the ground with electrical tape to allow Meshroom to grab more reference points. As a result, the Meshroom model was more complete and contained all the relevant geometry. Blender was then used to remove the background geometry and make the model manifold. A decimate and smooth modifier were added, as initially the geometry straight out of Blender was intended for importation into ANSYS. After some trial and error, the method shown here was used to import the geometry into ANSYS CFX. A mock wind tunnel was then created and a Boolean cut operation used to cut the motorcycle out from it. Unfortunately, at this stage, the quality of the model was too complex and the resulting geometry was not able to be reasonably meshed in CFX. To remedy this, the STL data produced by the photogrammetry process was used as a reference to build some simpler geometry, shown here. It's a close approximation that will be much more computationally friendly to process on the CFD side. The fairings were made using the inbuilt Creo Freestyle tool. The geometry was combined with other parts in an assembly, allowing separate models of the rider and winglets to be later added and adjusted easily to explore different cases in CFX. This was the original data used to select an airfoil profile for the wing. The data was collected from a website called airfoiltools.com, which is a database full of various shaped airfoils. As brought up in the Part A conference, the CL to CD values are abnormally high here. And after some investigation, it was found that airfoiltools.com uses a program called Xfoil to calculate the coefficient of lift and coefficient of drag data using a normalized chord length of 1 meter. This is in an attempt to make comparison simpler. This, however, raises a problem because the original airfoils used for comparison were selected based on their local Reynolds number at the winglet, which does not have a chord length of 1 meter. So after dividing the original Reynolds number by the chord length and reassessing which airfoil profiles would have the highest coefficient of lift to drag ratio at this new Reynolds number, the airfoil previously selected was no longer viable. A new airfoil shape was selected and a simple CFD test was conducted to confirm the findings about Xfoil's normalized calculations. As a result, the new B24 airfoil has approximately a 15% higher lift to drag ratio at 50 meters a second and a much more reasonable lift to drag ratio overall. When adjusted to have a normalized chord length, the data matches the airfoil tools data. Due to the New South Wales COVID-19 restrictions, access to the university was not possible and the project was rescoped in the testing department. However, I still wanted to attempt some physical tests, and this meant all the manufacturing had to be completed at home. So I purchased a cheap, readily available, fairly popular 3D printer in the hope that if any troubleshooting was required, it would be fairly quick. First, a pair of the E63 winglets were printed, the original design. This was before the Xfoil analysis. After the analysis, the new B24 airfoil was selected, the winglet was remodeled, and a pair of them was printed. This time, some slight design changes, including placing the mounting hole directly on the chord line of the airfoil and squaring the end plate to it, allowing for easy measuring of angle of attack when setting them up on the bike. In order to move the winglets, I researched and constructed a basic control system with an Arduino, taking a voltage signal from a differential pressure sensor and pitot tube, and then mapping that data to move two servo motors accordingly. Here's a bench test for a proof of concept before it was wired up and installed on the bike. So there's a fan going there, differential pressure sensor into the Arduino, and then as a result the position is mapped, so you can see that's the airspeed changing. This moving the pitot tube in and out of the airstream to change the speed, and then the angle is changed accordingly. Next was the process of mounting the winglets to the servos on the bike. As can be seen, anywhere on the front of the bike where the winglets could be mounted would have the airflow directly impeded from the indicators. A neat workaround was to use a second pair of cheap mirrors and install indicators into them, running the wires through them and wiring them in. A small piece of the inner fairing was trimmed out to make room for the servos. And initially a cardboard mock-up bracket was made to give an idea of routing and mounting points. The radiator side mounting point here had to be drilled and tapped to match the left-hand side. Based off the cardboard mock-up, a Creo part model and drawing was produced to give the required cutting list of material. The pieces for the bracket were then cut out of 25 by 3mm mild steel bar, as it is readily available from Bunnings during lockdown. Small standoffs were then cut from 12mm aluminium tube and used to clearance for the front mounting point. Once the pieces were roughly cut to the correct lengths and angles, they were bent and tack welded, shown here. Fitment was then checked again, and once correct they were fully MIG welded and any sharp edges cleaned up, then painted to prevent corrosion. This was all completed at home with basic tools such as an angle grinder and MIG welder, as once again, due to lockdown, access to the university was not possible. On the electrical side, a voltage converter was used to take the bike's 12 volt power supply and turn it to 5 volts to power the servo motors separately from the Arduino, as the Arduino couldn't supply enough current on its own. The Arduino and differential pressure sensor were temporarily mounted to allow ease of accessibility while testing, and fully installed. To make it easy to see the servo angles, a piece of sticky tape was placed on the fairing behind the winglets to measure the appropriate angle. The angle of attack could be measured from the top of the end plate here, as its edge is parallel to the airfoil's chord line. Initially, some thick bricklayers string was attached to the wing to visualize the flow. However, this was eventually swapped out for some much thinner sewing thread, as it was affecting the flow over the airfoil surface. Also shown here is just a pre-ride test to make sure that it was working. This is the recording setup for the video, just looking at the airfoil from behind. This is the first test. You can see the thicker pink string is a fair bit bulky and too long, as it's getting caught up in the wake as well. You can see the angle of attack changing with the vehicle speed as well. This side-by-side video comparison with the smaller sewing thread shows the different separation points. This video on the left is set at a constant angle of attack of 15 degrees, which is beyond the efficient lift-to-drag ratio. The video on the right shows the system changing angle in use, maintaining the optimum lift-to-drag ratio. You can see the separation is at the rear of the airfoil here, whereas on the set angle it happens sort of further down. At the start of the project before lockdown, the plan was to print a scale model of the motorcycle fairing and test the system in a wind tunnel, measuring lift to drag at various angles with load cells. However, once again, due to the COVID-19 lockdown, access to the university was not possible. So this data is going to be compared to the CFD model of the system once it's verified, and if the same flow patterns are observed and flow separation occurring at the same points for relative angles, the actual lift to drag forces experienced should be similar to the ones modelled in CFD. Thanks for watching. If you have any questions, leave them in the comments and I'll answer them in the poster defense session. Cheers.